cycle: fetch, decode, execute, store. And I had to break it down like that because some of these steps aren't obvious. Decode sounds like, when you hear decode, you're like, do you get the instruction in a code? Is it like encrypted? Not necessarily, not really. It's just, it's the CPU taking the outside language, I guess, of however the instruction is given. It's given in an instruction set architecture, and then it's broken down into internal steps to understand. Into like Intel micro-ops and AMD maker-ops, and then other stuff with AMD and RISC and Cisco. It's very messy, but decode is very hard to understand what's being done if you just hear the word, but when it's being broken down, explained like this, then you're like, okay, I got it, you know. Gets it, and it's trying to break it down into stuff I can do. Got it. Okay, machine cycle, very important. Really, that's why I had to like dedicate so much time to it. This video is gonna go way longer than I thought. Fourth, clock rate. This is kind of a weird concept. Why do we even need clock rate? Some people may ask. If you're thinking out of the box, you're gonna be like, why do we even have this? Why doesn't everything just happen instantaneously? It's kind of like, again, I'm gonna make an analogy to a car. Let's say you have a car and one piston is traveling in your engine way faster than the others. That physically can't happen first, but let's say it did. It would break instantaneously because it would snap off the I can't remember the term for some reason. I took engineering, or not engineering. I took automotives in high school. Crankshaft. There we go. Piston break off the crankshaft. There we go. That would work. CPU is similar. Everything needs to electrically line up. Some parts or some systems of the CPU, if they're all running at the same clock rate, and one part of that system is electrically running faster, it physically can't work. Because let's say you have a queue, and let's say you're a decoder, and there's a queue next to you, and you're faster than your queue in clock rate, and you're just, you know, shoveling stuff into a queue that can't take it, but since you're operating faster than the queue, you're giving it anyways. It doesn't work. You have to have a governing rule. Some parts of the CPU can't run as fast as other parts, and you know, there is like individual core clock, and even in some older CPUs and some designs, you would have the Pentium 4 had an ALU that ran twice the speed of the rest of the CPU. But that worked because of how it's designed. Clock rate is necessary for the CPU to function. If it doesn't have clock rate, things would have, like, there'd be electrical collisions first and foremost. That'd be bad. You would have compatibility errors because you might plug in like a GPU that would have no clock rate of its own, and it would get shoved instructions from the CPU so quickly, or so like not quickly enough. You need clock rate, really. Anyways, back to the point. That's why we need it. What is clock rate? Let's say, back to the student analogy. Let's say you are a student and you work at 1 hertz. You do one thing per second, 1 unit of work per second. And let's say you have 7 steps. Hold on. You go to the art store, get your stuff, go home, look at pictures, do the picture, and get ready. Okay, you have 6 steps, not 7. And let's say all of these steps take 1 unit of work. So you have 6 steps. This might fall. It's really not put there very well. You have 6 steps, and you work at 1 hertz. You have 6 units of work, and you can do 1 unit of work per second. How many seconds does it take to finish? If you guess 6, it's very intuitive. You got it. Let's say you're running at 2 hertz now. How many steps does it take to do that? 3, because you're doing twice the work in the same time. You're running twice as fast. However, let's say you have another friend in that class, and he breaks it down. Let's say he already has art supplies, actually, at home. He's going to be running faster than you, even if you're running at the same clock rate. That's why it's important to kind of not confuse clock rate between designs. Looking at like an AMD CPU, like an 8320, it runs at a certain clock rate. I honestly can't remember. I think it's like 3.8, 3.9, or I think it boosts up to 4, somewhere around there. And then comparing it to an old Pentium 4 that runs at like 3.8 gigahertz, even though they have very similar gigahertz or same clock rate, they don't run even in the same world of performance. Same thing with like an i5 4690K. Not even the same planet, not the same universe. You can't use clock rate to compare processors of different designs. Sure, if you have an i5 4690K and your friend has an i5 4690K and yours is 4 GHz and his is 3 GHz, yours is probably faster. They're the same design. They're both off Haswell. Haswell refresh, to be more specific, but they're both Haswell. But if your friend has a Core 2 Duo and you have your Haswell, not comparable at all. You can't compare them. Not even within the same company, not across companies, not across, like, they have to be the same architectural design. And even within the same architectural design, you get discrepancies, because one CPU might have more cache, one might have hyperthreading, one might have an IGP, which is important to you, one might have a different IMC. You have to compare on a very equal playing field for clock rate to matter, which is why clock rate as a concept for comparison is not very good. It's very important to understand the concept and how it works in a CPU, but it's very hard to use as a means of comparison. Some people will be like, 1 Intel Hertz is equal to like 2 AMD Hertz or something like that. I've heard that before thrown on forums. That's not correct. And I mean, it's not so pervasive anymore, but it's definitely not correct. It's going to be a very long video. I apologize. I should break this up into 2 parts. Anyways, so that's clock rate. Next, cores. This picture I drew to represent that. Let's say you are let's say you have a 4-core CPU. If you give it 4 instructions, intuitively and humanly, you would give one of those instructions to 1 core, so you would have 1 instruction per core. That's right. Or intuitively, that sounds right. Let's say you have 4 classmates, or let's say you're in a class of 4, and the teacher wants 4 paintings of boats. Intuitively, you would give 1 to each of the class, 1 assignment to each classmate. Sounds intuitive, sounds fine. Unfortunately, you don't get to choose that. If you're running a program, let's say you're firing up a game. I'm not going to name a game because there's so many out there, and if I say League of Legends or CSGO, okay, I already did. If you don't get to choose what the software is used, some softwares operate off 2 threads. Some softwares operate off unlimited, it just keeps scaling up. Some operate only off 1. And the reason for that is because some softwares operate ideologically better on 1 thread. They don't use many resources, or they need a serial amount of a very serial execution, or some operate better having different cores or different threads work on different things, and then they all coalesce together afterwards. So sometimes, you may have a CPU. You may have a dual core CPU. I don't think they sell single cores anymore. I'm almost damn sure they don't. And let's say you have a software that supports 8 threads. I think Crysis 3 supports 8 threads. Could be wrong. It's been a while since I've looked. Your dual core will still support the game, but it's like having 8 classmates, it's like having 8 assignments be given to 2 classmates. And then they work the other way around too. Even though you have 4 cores, if you only need 1 painting done, you're not going to use all 4. You only use 1. Or let's say the teacher asks for 80 assignments. He might give all the 80s to this guy. These other 3 guys might just get to sit at home and watch TV. It's all down to the software. Buying a CPU with more cores does not always result in better performance. So conceptually, what is a core? A core is just an implementation of a system repeated over itself. It's kind of like they copy and pasted a core and then put it side by side, but it's not exactly that simple because of the uncore and how everything interacts. So it's not copy and pasting, but basically it's how many iterations of that system exist on the die, on the CPU itself. And you can't compare an FX8020, an 8-core system, to an i5 4690K, a 4-core system. The two are completely different designs, and if you look up benchmarks, they get very different results in benchmarks. They're just completely different. So, with these 2 things in mind, there is a very important myth or misunderstanding that's been going around for a very long time. It's not too bad now, but trying to determine computer or CPU performance by taking clock rate and multiplying it by core count. Please don't do this. I can't say it enough. Again, the software determines how many cores it will use, and clock rate from one design to another may be completely different. It's really, you can't do that. It doesn't work, quite simply. I mean, if you're going off the same design, if you have like a dual core Haswell at 3 GHz and then you compare it to a 4 core Haswell at 4 GHz, you're probably going to get higher performance on the 4 core. But if you try to compare it across designs from different designs, it doesn't work, quite simply. So I'm probably going to break this video into 2 parts, unfortunately. I was not expecting it to go to the song, but yeah, so what we've learned today. Series restarted. I'm gonna do it again. I'm gonna finish it, or at least I'm gonna promise myself I'm gonna finish it. Hopefully we'll be able to finish it. It's gonna be better. It's gonna have this handsome, beautiful face. I'm joking. On camera, it's gonna have the whiteboard. It's gonna be better. It's gonna go over stuff in more depth and more understanding. So you make sure when you sit down, you're going to learn something. If you don't know much about it, you might already know this. This is basic stuff, but you're going to get something out of it. Disclaimer: I don't know everything. I might be wrong. Sometimes. But most of the time, probably going to be right. Or at least I know a lot. You're going to learn something, probably. Machine cycle, fetch, decode, execute, store. We learned that. Base stuff. Clock rate, we understand why we need it, what it does, how it works. You know, if you're working at twice clock rate on the same design, you could get about double performance. Again, it's really software driven. It's very complicated. You know, doubling clock rate doesn't mean double performance. It's all down to like bottlenecking and how software operates in other systems and the right. Anyways, and then cores, what they are, why you can't multiply clock rate by cores, how software interacts with cores. It might give you more, it might have more threads in the software than there are cores on the CPU, or supported threads on the CPU. There might be less. It's really up to the software. And that's really all. That's all we learned today. So yeah, you know, it's been nice doing this video again. It feels really good. So see you next time.